Welcome to The Explainer. Today, we're tackling a problem that might seem really small, but it has absolutely massive implications for medical research. We're talking about converting units. Now, you might think that's simple, but it's a surprisingly tricky puzzle. The good news? Modern technology is finally cracking the code, and it's making drug development a whole lot faster and safer. So let's start with the big question. Why is something like converting milligrams per deciliter to millimoles per liter such a huge deal? Well, in global clinical trials, precision is absolutely everything. You've got data pouring in from labs all over the world, but if that data doesn't speak the same language, you can't compare it, you can't analyze it, and you definitely can't use it to get a life-saving drug approved. For years, getting this wrong has been a major source of errors, delays, and just massive headaches. Okay, so let's really dive into this data puzzle. For the longest time, standardizing all this information was a slow, manual, and really error-prone process. But now, a combination of much smarter standards and modern tech has created this really elegant solution that is completely changing the game for scientists and data managers. Here's our roadmap for today. First, we're going to unpack that clinical data puzzle. Then, we'll meet the two key standards that provide the solution. After that, we'll look at the digital translator that does all the heavy lifting, see it all work in a real-world tool, and finally, we'll look ahead at what this all means for the future of medical data. All right, let's get started. To really get it, we have to go to the heart of the problem. Why have units been such a constant, nagging challenge in clinical research? So picture this. You're running a huge global clinical trial. You get blood glucose results from a lab in the US, measured in milligrams per deciliter. At the same time, you get results from a lab in Europe, and they're in millimoles per liter. To make any sense of this, every single one of those values has to be converted into a standard format. In the clinical world, that's called SDTM. The final number goes into this one specific variable, strES. For decades, this meant a person had to manually look up conversion factors and write custom code for every single test. It was tedious, it was expensive, and honestly, it was a recipe for disaster. The old way of doing things relied on a standard called CDISC controlled terminology. But here's the catch. It was basically just a dictionary. It would tell you that inches is a valid unit and cm is a valid unit, but it had no way for a computer to understand the relationship between them. It was a vocabulary list without any grammar. So trying to automate conversions, it was pretty much impossible. So how did we move past that? Well, the solution wasn't about trying to fix that old dictionary. It was about bringing in two new, much smarter standards. Let's call them the librarian and the mathematician. So, meet our two heroes, LOINC and UCUM. Think of LOINC as the universal librarian. Its job is to assign a unique, specific code to every single medical test you can imagine. And this is a big deal. The FDA actually requires these codes now, so every test is identified in exactly the same way. And then you have UCUM, our master mathematician. UCUM is a global standard for units that was built from the ground up to be a system. It doesn't just list units, it actually understands the mathematical relationships between them. This slide really gets to the heart of the difference. The old way, CISCT, would just have mmGHG on a list. But UCUM, the system, uses this specific notation, mmHg. Now, that subtle difference in brackets, it's everything. UCUM's grammar lets a computer understand, oh, this is a unit of pressure, and then it can programmatically convert it to pascals or bars or whatever. CDISCT just can't do that. It is literally the difference between a simple list of words and a whole language. Now, lucky for everyone involved, there is some good news. For a lot of the really common lab units like mg/dl, the text just happens to be exactly the same in both the old list and the new system. And this little bit of overlap makes the transition to this smarter way of doing things way, way smoother. Okay, so we have our librarian to identify the test and our mathematician to understand the units, but how do we actually get them to talk to each other and do the work for us automatically? Well, that's where the digital translator comes into play. All this work is done by something called a RESTful Web Service. Now, don't let the techie name scare you. Just think of it like a super fast, dedicated messenger for computers. A program on your machine sends a very specific question over the internet, something like, hey, convert 2.5 milligrams per deciliter to millimoles per liter for glucose, and a special server on the other end instantly sends back just the answer, all packaged up in a nice, simple format. And here you can see it in action. A tool sends a request to the web service asking it to convert 2.5 milligrams per deciliter of glucose using its unique LOINC code. The service then shoots back this block of code. Now, I know, it looks a little complicated, but it contains one simple, absolutely crucial piece of information.
And that crucial piece of information is this number right here, 0.139. The computer program just grabs this value from inside a tag called result quantity, and boom, the conversion is done. No lookup tables, no manual calculations, just an instant, perfectly accurate answer. All right, so let's see how all this theory comes together in a real-world software tool that's actually designed for handling clinical trial data. So a tool like this one, SDTM-ETL, builds these web services right into simple, powerful functions. A data programmer can use a basic function for easy stuff like inches to centimeters, or they can use a more advanced one that uses that LOINC code to handle the really complex lab conversions. And there's even a backup function for those times when you don't have a LOINC code, but you happen to know the molecular weight. It's got all your bases covered. So here it is, the perfect before picture. If you've ever worked with this kind of data, this probably looks painfully familiar. You can see different test results, but the units are just all over the place. Some are conventional, some are already SI units. Trying to analyze this dataset as is, it's pretty much impossible. And here's the after. Just look at that column LBSTRSU. With a single automated command that calls the web service for every single row, the tool has perfectly converted every value to the correct SI unit. The result is a clean, consistent, analysis-ready dataset. The difference is just night and day. But what's really cool is that this system can take the guesswork right out of the equation. Instead of telling it what unit to convert to, you can just ask it. With a simple function, you give it the LOINC code for a test, and the service will tell you what the correct standard SI unit is supposed to be. It automates not just the math, but the decision-making process itself. So what does all this automation really mean for the future of medical research? Because the implications here are way bigger than just saving a little time. You know, this quote from the source material really just sums it all up. Having these LOINC codes combined with these web services is a massive leap forward. We're moving from a world of painful, manual data mapping to a world of intelligent automation. And that means data gets processed faster with far fewer errors, which lets researchers get to the actual insights that much more quickly. And it's so important to talk about security and privacy here. Throughout this entire process, no patient-identifying information ever leaves the system. The only things that get sent to the web service are the numbers and the units, things like 2.5, mg/dl, and a LOINC code. The process is fast, it's accurate, and it is completely secure. When you really step back and look at it, what this technology does is solve a fundamental problem of communication. It gets different data systems to speak the same language fluently. It's a true universal translator for scientific units. And that leaves us with one final thought. Now that we've cracked this code, what's the next great communication barrier in science that we can break down using the same kind of thinking?